Yeah, so good afternoon, everyone. Today we are going to discuss about the week 10 assignment, which is assignment 10 of the previous year of the basic electronics course E62 NPTEL tutorial course. As you all know that the Professor Mahesh B. Patil is taking the course. He is the instructor, and myself, Mr. Subhajit Basak. I am a PMRF fellow from IIT Bombay, and this is the 10th lecture actually which I am giving about the NPTEL tutorial. So as you all know, the meeting schedule is from every Tuesday from 6 p.m. to 8 p.m. Okay. So yeah. So let me turn off the video and then I will discuss. Okay. Yeah. People page. Okay. So let me share my screen. Okay. Yeah. Yeah. So so far we have studied till lecture 9, that is the week 9 assignment 9, which is consist of the analog electronic course. So okay, yeah. So we have so far dealt with analog electronics course. In the analog electronics, we first we first discussed about the diode, and then from diode how the BJT works, the bipolar junction transistor, and from there we have moved on to op amp, operational amplifier, and some basic Bode plots, and after that we are moving towards the digital electronics. So this is the basic thing which is digital electronics, which is equally important as analog electronics. Okay, so this is the thing, digital electronics. So mainly the digital electronics is confined of these two part. One is the combinational logic circuit, which is combinational circuit, and other one is known as sequential circuit. So the basic difference between the combinational circuit and sequential circuit is that in the sequential circuit we have a use of memory, and in the combinational circuit there is no use of memory. So in case of combinational circuit we can say that the present output is a function of present input only. That much, that means that whatever we are giving the input, based on that we are getting the output. This is the meaning of the combinational circuit. And for the sequential circuit, the basic difference from combinational circuit is like that the present output is a function of present input, present input. Okay, yeah. So present input, as well as it is a function of past input, as sorry, past input, and as well as it's a function of past output. So we can say that the present output is not only depends on the present input, but it also depends on the past condition. Maybe it a past input, or maybe it can be a past output. So the this is well known as a memory thing, right? In the memory, what we do, whatever was the previous thing that we just memorize, and then based on that the present output will perform, right? So this is the basic difference between the combinational circuit and the sequential circuit. So in case of combinational circuit, the basic elements that forms the combinational circuits are the logic gates. So logic gates are the basic things. That means the AND gate, OR gate, NOT gate, and also there are some basic apart from basic gates there are some universal gate, that is NAND and NOT, and also some special gates, XOR and XNOR. We will discuss one by one everything. Okay, and in case of sequential circuit, the basic elements is the flip flop. So this is the basic memory element. It is known as a flip flop. So this is basically based on the clock. Okay, in the sequential circuit it is based on clock. Okay, Each and everything is based on clock. After each clock pulse, the output got changed, but in the combination circuit, it's not based on the clock. Okay, yeah. So these are the basic things. So mainly in this week 10 assignment 10, we will focus only on the combinational circuit part, combinational digital circuit or combinational logic circuit first, and then in the next lecture, week 11 lecture, we will move on to sequential circuit. Okay, yeah. Okay, so let me discuss few things at first, and then I will solve each of the assignment question of the previous year. Okay, yeah. Okay, so now I will move on to the digital electronics, and from here it is the combinational part. Okay, combinational circuit. Okay, yeah. So in the combinational circuit we have few things. First one, we want to discuss about some logic gates, and then we will do some Boolean algebra, and then we will do some K-map problems, and then the basic thing like multiplexer, demultiplexer, lot of things are there like decoder, encoder. So these all are under the combinational circuit part. Okay, yeah. So I will start one by one. First one is the logic gates. So in the logic gates, there are three types of logic gates. Okay, first one is the basic gates. Second one is the, we can say, universal gates, and third one is the special gates. Okay, special gates. Okay, so in case of basic gates, there are three kind of gates like NOT, and OR. Universal gates, there are two type of gate like NAND and NOR. Okay, and in the special gates, there are XOR and XNOR. Okay, these three types of gates are there. Okay, so basically at first I will discuss something about the NOT gate. Okay, yeah. So NOT gate, in the NOT gate, the basic symbol of the NOT gate is like this. Okay, so there is a bubble at the output, which means that it works as an inverter. So whatever be the input, let's say A is the input, then the output will be Y equal to A bar, that is the complement of A. Okay, so if we draw the truth table A and Y equal to A bar, then we can say there are actually two number of input possible for A. One is 0, another is 1. So if the input is 0, the output will be complement of that 0, which is 1, and here it will be the complement of 1, which is 0. So this is the basic truth table of the NOT gate. Okay, so this is the NOT gate. Yeah. Okay, the second gate is basically the AND gate. The symbol of the AND gate is like this. So this is basically two input AND gate. It can be more than two input. There can be more than two input also. Okay, so I am taking a basic example of two input AND gate. Let's suppose A and B are the two input of the AND gate and Y be the output. So Y can be written as A multiplied with B. Okay, A dot. So if we write the truth table of this AND gate, then we get, so there are four possible combinations are available for this, right? A and B. One is 0 0, other one is 0 1, then it can be 1 0, and then it can be 1 1. Okay, so you can see that it is a simple multiplication of A and B. So 0 multiplied 0, it can be 0, it will be 0, this will also be 0, this will also be 0, and this will be 1. So the physical significance of the AND gate is basically the AND gate output becomes 1 whenever all the inputs becomes 1. Okay, or we can say in other way, that the AND gate output will become 0 when any one, remember this thing, any one of the input becomes 0, right? So here A and B both are 0, so it is output is obviously 0. Here 0 and 1, any one of the input, that is A, is 0, so the output is 0. Here B is 0, output is 0. But when all of them, all of the input A and B both will be 1, then the output will be 1. So this is the thing, basic thing, AND gate. Okay, so we can also extend this formula, or uh, extend this logic for several input, suppose n input AND gate also. Okay, yeah. So the third gate is basically the OR gate. Similarly, I am giving the example of the two input OR gate, and the basic symbol of this OR gate is this thing. Okay, so there is A and B, both the input, and the output will be A plus B. Okay, so if we draw the truth table of this, y equal to A plus B, so this is 0 0. Similarly, the four combinations is available, as I have already discussed, 1. Okay, so the output 0 plus 0, it will be 0, it will be 1, it is 1 plus 0, it is 1, and it is 1. So this means that the output of the OR gate will be 0 if all the inputs are 0. Remember this thing. Okay, and the output of the OR gate is 1 when any one of the input is 1. Got it, right? Yeah. So this is the basic gates. These three are basic gates. So remember, any of the Boolean functions, any of the Boolean function means, suppose here it is say AB plus C bar D. Suppose this is a logic function, we have to implement this thing. So this is known as a Boolean expression. Okay, Boolean expression. Okay, this is a basic Boolean expression. Okay, F equal to AB plus C bar D. So suppose we have to implement this Boolean expression, then we have to use some kind of gates, right? So what can be here? It is AB, so we should use 1 2 input AND gate, A B, this thing, and then C bar D, so we should use, so here if we have input C, so we should use a NOT gate so that it can turns into C bar, and then we have another input which is D, and then we have a OR of that. Okay, plus sign, that means OR of that. So we are using OR. So this is AND gate, and this is AND, this is OR, and this is NOT. So basically, any kind of Boolean functions, any kind of Boolean expressions or Boolean functions can be implemented by using these three gates: NOT, and then AND, and then OR. So these three are basic gates. So that's why it's called the basic gates, because it is the basic gates using which, basic logic gates using which we can implement any Boolean expression or any Boolean functions. Okay, so this is the first part, and next we'll discuss about some universal gate. Okay, yeah, okay. So now I will discuss about some universal gates. Okay, yeah. So these are the all basic gates. Okay, okay, yeah. So now, what are the universal gates? Just there are basically two types of universal gates that we generally use, which is, one is the NAND gate, NAND, and another one is the NOR. Okay, so I will discuss NAND first. Okay, so two input NAND gate I will discuss NAND. So the symbol of the NAND gate is basically nothing but AND followed by NOT. So suppose this is a and if we follow this NOT by this, then this whole thing will become the NAND. Okay, so this can be represented as, so this is A B bar. So this thing can be represented by this symbol. We take the bubble inside this thing just after this AND gate, so it becomes the NAND symbol. Okay, so y equal to A B bar. So if we write the truth table of this NAND gate, at first what is the AB, and then we will write y equal to A B bar. Okay, so 0 0 0 1 1 0 1 1. Okay, so what will be the AB? 0 0 0 and it is 1. So it will be complement of this AB, right? So 1 1 1, then it will be 0. So this means the NAND gate output will be 1 when any of the input is 0. Okay, and the NAND gate output will be 0 when each of the input is 1. Okay, so this is the physical significance of this NAND gate. Okay, and similar to the NAND gate, we have one more gate which is known as NOR gate. So NOR gate is basically the same thing, which is OR gate followed by a NOT gate. Okay, so suppose this is a OR gate, there are two inputs. So I am discussing about the two input NOT gate. So suppose A and B are there. So here the output will be A plus B bar. So if we rewrite this symbol using this, so this is a basically NOT gate symbol. Okay, so it will be A plus B bar. Okay, so A, B, and if we write A plus B, the truth table basically y equal to A plus B bar. So truth table is basically what? Truth table is basically a table that displays that for each of the input combinations of the input, what is the corresponding output. Okay, so there are 4 combinations possible, and for A plus B, the first one will be 0, rest other should be 1, and it should be in complement of that, so that is like this. Okay, so the physical significance of the NOR gate is basically that if we have both the input as 0, then the output will be 1, otherwise the output will be 0. Or we can say that if any of the input is basically 1, then the output will be 0, otherwise the output will be 1. So this is the physical significance of the NOT gate. So why we use these two gates, NAND and NOR gates, why it is called as a universal gate? So because basically the basic gates are needed to implement any of the Boolean functions, right? But it is called, this NAND and NOR gate are called universal gate because using these two gates we can form any kind of gate. Okay, so I will discuss that one, but at first I will focus on the special gate, and then I will tell you that why this is known as NAND and NOR is known as the universal gate. Okay, so at first I will go for the special gates. Okay, special gates. Okay, so in the special gates, first kind of gate is XOR gate. Okay, XOR gate, the symbol of the XOR gate is like this: A, B, and this is Y. So this Y can be written as A bar B plus A B bar, which is A complement B plus OR of A B complement. Okay, so if we write the truth table see, this is 0 0, this is 0 1, this is 1 0, this is 1 1. Okay, so this can be 1 1 0 0, this is 1 0 1 0. Okay, now if we do a bar b, a bar, that means 1 into 0, this counts as a 0, this come will be 1, this will be 1, this is 0. Yeah. So we can see that in this part the output will be 1. Okay, so that means if the inputs are unequal inputs, if there are unequal inputs, then output equal to 1. So XOR gate is often known as inequality detector. Inequality detector. Okay, so that means whatever is the output, if the inputs are unequal, then we can say that the output will be okay. And the second thing we can notice that odd one detector, that means here for 0 and 1, here the number of 1 is 1, right? There is only one number of 1. Here is also there is one number of 1. Here is 2 number of 1, and here is 0 number of 1. So if there is any odd number of 1, then it can easily detect that thing. Easily detect means the output will be 1. Okay, so the XOR gate is also known as odd one detector. So this is the basic thing. Okay, next I will move for the XNOR. Okay, XNOR. So for the XNOR gate, the symbol is, so XNOR is basically XOR gate followed by NOT gate, followed by NOT. XOR gate followed by NOT. Okay, so this is a XOR gate, and if we add a NOT gate or an inverter over there, then we can get a bar b plus a b bar, this complement. Okay, okay, I forgot to tell one thing, that this XOR, it can be referred by this symbol. This is a XOR symbol, this is known as XOR symbol, the plus sign. Okay, inside the circle. Okay. And here also, if we combine these two, we get a b, and this is a y, which is basically the complement of XOR, right? Here also it is the complement of XOR. Okay, so this is the complement of XOR, and it can often be written as a cross b or a dot. Okay, so if we expand this thing, we get ab plus a bar b bar. Like here, XOR gate, we got a bar b plus a b bar, but here ab plus a bar b bar. Okay, yeah. Okay, so I will show this how we get ab plus a bar b bar. So basically, the XNOR operation is a XOR b this bar. Okay, so that means a bar b plus of a b bar, this whole bar. Okay, so using the De Morgan's law, we have another law which is known as De Morgan's law. I will discuss this. Okay, better I will discuss the De Morgan's law, and then I will write this equation. using how we can get the x naught expression. Okay. Okay, so I have discussed about the special gates. Now, okay, now I have to discuss about the truth table of the x naught gate. So this is a b, and similarly it is the a bar b bar, and now it will be y equal to ab plus a bar b bar. Okay, yeah, so it will be 0 0 0 1 1 0 1 1, so it will be 1 1 0 0 1 0 1 0. Okay, and here it will be 1, it will be 0, it is 0, it is 1. So we can see here the output will be 1 for this case and for this case, the last one. Okay, for these two cases. So that means whenever the inputs are equal, this is 0 and 0 equal, 1 and 1 equal. So for equal inputs, the output will be 1. So that means the x naught is often known as equality detector. Equality detector. Okay, equality detector means it detects the it detects the equal input. Detects means the output will be 1 whenever the inputs are equal. Okay, yeah. And similarly it is known as even one or even parity one detector. That means, see here, there are number of input is 1. Okay, the number of input 1 is 1, the number of input 1 is 2, and here also the number of input 1 is 0. So that means when there are even number of 1, then it will, the output will be 1. That means it will detect the even 1 as the input. Okay, so these are the special gates. Okay, so these are the basic things about the special gates. Now I will discuss about the few more things about these gates, which is, suppose in case of XOR gate there are 3 input. So 3 input XOR gate, then how it will be the output? So there are 8 combinations possible: 0 0 0 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and then it will be 1 1 1. So the output will be, so here there are odd number of 1, so the output will be 1. Here odd number of 1, the output will be 1. Here the odd number of 1, the output will be 1. And here the odd number of 1, the output will be 1. But here even number of 1, it will be 0. Even number of 1, it is 0. Here it will be even number of 1, it is 0. Right? And one more 0 is here only. Okay? Even number of 1, it is 0. Okay? Similarly for XNOR gate also you should see like this. So remember one thing, for odd number of inputs the XNOR is same as XOR, but for even number of inputs the XNOR is complement of XOR. Complement of XOR. So you can write that A XOR B, it is a complement of this. Okay, but in case of 3 input, if there are odd number of input, then this XOR is basically same as this XNOR is basically the same as XOR. Okay, so these two things you should remember. Okay, if you actually elaborate the expression, then you will easily understand, you will get the same thing. Okay, so these things are equal. equal things, the same things. Okay, so this is the basic thing. Now I will discuss why these gates NAND and NOR are called universal gates. Because using NAND and NOR we can implement any kind of gate. Suppose we are considering NAND gate at first. Okay, suppose we are considering NAND gate as first. So NAND first as NOT gate. How we can use NAND gate as a NOT gate? So NAND gate symbol is like this. This is the NAND gate symbol. So if we fetch both the input here, then the output will be A dot A bar. So that means A and A is A, that is A bar. This is the NOT gate. Similarly, if we use this as a AND gate, how we can use? So we have two input A B. Here the output will be A B bar. But if we fetch this A B bar into one more NAND gate, then it will becomes A B bar dot A B bar whole bar. That means A B bar, that means A B. So this is a NAND gate. Third thing is as OR gate. As OR gate, how we can use? As OR gate, we can use it like, suppose Y OR means A plus B. If we put both side complement, then we get using De Morgan's law. I will discuss De Morgan's law, AB1. So that means we have two NAND gate to get complement of A and complement of B. If we put A, it will get A bar. If we put B, we get B bar. And then if we put this as the input of a NAND, next NAND gate, then we'll get this. That means A plus B. So which is basically the OR. So using NAND gate, you can easily write any of the gates. So NAND gate as XOR gate, if we want to write. So this is the basic thing. If we have A, if we have B. So see one thing. So you must know also Boolean expression, how it is used, and what is the basic Boolean algebra to solve all this question. Okay, yeah. So basically it is used as XOR gate like this. Suppose there is A, so this is A, and this thing is A B bar. Okay, this is A B bar and this is B. So here the output will be here, at here the output will be A dot A B bar whole bar. Okay, and here also the output will be B into A B bar whole bar. So if we expand this thing, that is A bar. Okay, so let it be like this. So here the output will be A dot A B bar dot B dot A B bar, and this is the whole bar. So that means A bar B, this bar, and again comes bar, plus B A B bar, this bar, again comes bar. Okay, so that means A into A bar B plus B into, sorry, A B bar. Okay, the whole thing A B bar. So that means A into, if we expand this thing, A bar B bar plus this, if we expand this thing, then it will be B bar. So A into A bar, this becomes 0. A into A bar plus A B bar plus B A bar plus B B bar. Okay, B bar. So this A bar, this is 0, and this is also becomes 0. So that means we left with A B bar plus B A bar, which is nothing but a XOR. So this is how the NAND gate is used as a XOR gate. So there we need 4 NAND gates, 2 input NAND gate to be to get a 2 input XOR gate. Okay. Similarly, if we want to use as XNOR gate, XNOR. Okay. So if we want to use a XNOR gate, then it will be the same thing we formed at first, the XOR gate. Then it will form XNOR gate. XNOR gate. So using this 5 2 input NAND gate, we get the XNOR gate. So till here we get the XOR, that means A XOR B, and after this we get A XOR B complement. Okay, so that means A XNOR B. Okay, so this is how the NAND we can implement the NOT gate using NAND gate, AND gate using NAND gate, OR gate using NAND gate, and XOR and XNOR. These two gates also using the NAND gate. So that's why NAND gate is known as universal gates. So similar is the thing for the NOR gate also. Using NOR gate also we can implement any kind of gate. So that's why it is known as universal gate. So these are some basic things about the logic gates. So I will not discuss about the how the NOR gate can be used as a universal gate. You can see in any book or any lecture and you can get that. Okay. So this first part is completed. So which is logic gates. Now I will discuss about some Boolean algebra. Okay, so this logic gates is completed and now I will use Boolean algebra, and K-map, marks, demarks, that I will cover using some example. We have already some previous year assignment question, so there we have to use the K-map also, K-map concept and the marks concept also. So there I will cover that how to use the K-map or the marks to solve any problem. Okay, but at first I will want to discuss some of the Boolean algebra things. So yeah, okay. So this is some Boolean algebra that I am going to discuss. Okay, so laws, there are some laws of Boolean algebra. First one is 0 plus 0, 0 plus 1, it becomes 1, 1 plus 0, it becomes also 1, 1 plus 1, it becomes also 1. Okay, similarly 0 multiplied 0, 0 multiplied with 1, 1 multiplied with 0, and 1 multiplied with 1. So 0, it will become 0, it will become 0, it will become 0, it will become 1. And also 0 complement is 1 and 1 complement is 0. So these are some basic things about the Boolean law. Okay. So there are one more thing which is known as AND law. AND law. Okay. So AND law is there, OR law is there, and NOT law is there. So what is the basic AND law? That means if A into 0, A into 1, A into A, and A into A bar. So A into 0, it will be obviously 0, it will be A, it will depend on A. If A is 1, then output will be 1. If A is 0, then output will be 0, right? A into A, that is A, and A into A bar, irrespective of input, the output will be 0, right? If A is 0, then 0 multiplied with 1, that will become 0. If A is 1, 1 multiplied with 1 complement, which is 0, that means 1 multiplied with 0, that will also be 0. So this is the AND law. For the OR, okay, so this output will be A, this is 1 plus a, that means it will be 1. This is a plus a, this is a, and this will be 1 again. Okay. For not means if a is equal to 0, then a bar will be 1, and if a is equal to 1, then a bar will be 0. And one more thing, a both complement, that becomes a. Okay. Yeah. So similarly, there are some other law also. One is known as commutative law. So the Boolean algebra follows the commutative law. Commutative law. So Boolean algebra follows some commutative law. That means if we do a plus b, so that is equal to b plus a. Okay. Similarly, if we do a multiplied with b, that means b multiplied with a. Okay. Or similarly, a b bar, that is equal to b a bar. This is the same thing. Or similarly, a plus b bar is equal to b plus a bar. Or if we do a XOR b, that is nothing but b XOR a. Both are same. Okay. A XOR b is equal to b XOR a. So these things are always same. So this is known as commutative law. Okay. Okay. So there are few other law also. One of them is distributive law. Distributive law. So in distributive law, we can say if there is a b plus c, then we can expand this by using a into b, which is results in ab, plus a into c, which is results in ac. So this is one distributive law. The second distributive law is a plus b and a plus bc. Suppose there is a plus bc, so that can be written as a plus b into a plus. So this is known as a plus bc. So this is one of the most important distributive law that we should remember, and it is true for the vice versa also. Okay. So suppose there is a plus d and then there is a plus e, so that refers to a plus de. So you should remember this thing also. So these things are basically known as distributive law. So these are some important things. Okay. Okay. uh, okay, so there are some few other laws. Okay, one of these is absorption law. So you should know about the absorption law, what it is. Suppose according to the absorption law, there is a into a plus b, then what will be the output? So the output is simply will be a. Or you can say if there is a plus ab, the output will be a. How it comes? See, if there is a plus ab, right? So what we can say, we can take a common and we can get 1 plus b. So as we always know that 1 plus something will result in 1. So 1 a multiplied with 1 and a multiplied with 1 it results in a. So this is this thing a. Similarly, if we expand this thing a into a plus b, that means a into a plus a into b, that means it is a plus ab. And similarly this thing a plus ab means if we take a common 1 plus b, that means a multiplied with 1 and that results in a. So this is a. Okay, so these things are known as absorption law. That means if there is a input and a multiplied with some other things, then these things are absorbed in the equation and it becomes only a. Okay, so this is the basic thing. And next other things I will discuss is consensus law. So what do you mean by consensus law? It is also very important law in the consensus law. So the consensus law says that if suppose a bar b plus bc plus ac, this is there. Okay, see the things correctly. Okay, so a bar b plus bc plus ac bar. So suppose there is one variable in which that variable and that complements are also present, then this expression will be minimized by a bar b plus ac. This bc will be vanished. Okay, right? Okay, I am giving one more example. Suppose AB plus BC bar plus AC. So there is one variable which is C, and there is another variable which is complement of that. So and the rest of the term belongs to other two variable, right? So it can be represented as like this. Okay, it can be reduced to like this. So this will get vanished. This will get vanished. This will get vanished. So this is known as consensus law. Okay. Yeah. And one more law is also there, which is known as associative law. So the associative law, if we discuss, so associative law means, suppose one equation is like this: a plus b plus c. Okay, that means at first we need to OR b and c, and then it need to OR with a, right? That means b and c will be OR at first, b and c, and then it will be OR with a, and then we get this as y1. Suppose y1, this is y1. Similarly, if we do a and b OR first, and then we will OR the c, that means a and b, a b OR first, and then we OR with c, then we get suppose y2. So these two are basically the same thing, same. That means we can interchange the order of this OR, okay, between the inputs. So this is one thing. Similar is the thing for the, suppose the AND gate, a plus bc suppose is there, so we can do ab then c. Similarly is the kind of XOR gate, b or c. If we do b or c first, or a or b first, nothing will matter, the answer will be the remain the same. Okay, and one more very important, the last topic is the De Morgan's theorem. De Morgan's theorem. So according to the De Morgan's theorem, a b bar, we get a bar plus b bar, or a plus b bar, that we will get a bar dot. These are the two things. This is also valid for any number of input. Suppose this the complement of this AND gate of this all the inputs can be written as a bar plus b bar plus c bar plus d bar plus dot dot dot, this thing. Similarly, if we do this thing, a plus b plus c plus d plus and this complement, so that can be written as a bar dot b bar dot c bar dot d bar dot dot. So this is the basic thing of the De Morgan's theorem. Okay, so these are the some Boolean algebra concepts that we have already discussed. So these two are the basic things. These two are the basic things. These logic gates and this Boolean algebra are the basic things to form the combinational logic circuit. Similarly, we will discuss the K-map thing also in the in solving some assignment problem and marks problem also, marks demarks decoder encoder problem also, solve this. Okay, yeah. So now we'll start to solve one by one. Okay, yeah. So in the first question, it is asked, consider the logical function x equal to p plus q plus r bar p bar plus q. Which of the following truth table correctly describe this function? So as I have already discussed, truth table means for each of the input combination of the inputs of the input variables, what is the corresponding output variable? If we list it down for all the input variable combination, then we can say it as a truth table. Okay, yeah. So here we need to expand this thing. X is equal to p plus q plus r bar, this thing, multiplied with p bar plus q. Okay, yeah, p bar plus q. So that means if we multiply this thing, so p multiplied with p bar, we get p into p bar plus p into q, p into q plus this q into p bar, which means p bar into q, okay, plus q into q, which is q into q, plus p bar into r bar, right, p bar into r bar plus q into r bar, right. So these things we have written using the this law, but associative law, okay, uh, sorry, distributive law, right. If a into b plus c is there, then ab plus ac, that will be multiplied. So using the distributive law we have written this thing, okay, yeah. Now we know p into p bar, that becomes 0, plus this is pq plus p bar q, q multiplied with q, that will become only q, and then p bar r bar, and then q into r bar, okay. Now if we take q common from this, one thing is from this pq, p bar q, then only q, and then q r bar. If we take q common, then we get q common, p plus p bar plus 1 plus r bar, okay, and the rest other thing is p bar into r bar. Now 1 plus something will always result in 1, so q into 1 plus p bar into r bar, right. So q into 1, that means q plus p bar r bar. So this is the final expression of x, okay, this is the final expression of x. Now whatever was the previous expression, we have simplified using some Boolean algebra laws, and using that law we have simplified to a simple equation, Boolean equation, which is x equal to q plus p bar r bar. Now we will see in where it got satisfied, okay, yeah. See, we can see tactically, right. See one thing I am showing you, yeah. So it is q, so that means x will be always be 1 when there is q is equal to 1, because 1 plus something, that will result in 1. So I will go with option, at first I will see the option a. In option a, wherever the q is 1, so here q is 1, the output is 1, so that is good. This is 1, output is 1, this is 1, output is 1, this is 1, output is 1, okay. According to the q, here if we see q is 1 but output is 0, that means it's not possible, okay. So this cannot be the answer. Similarly here, this is 1, 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 but this output is 0, so that cannot be possible, this cannot be the answer. Here also this is 1, the output is 1, this is 1 but the output is 0, so it cannot be the answer also. So the correct answer will be option a, right. See one more thing also, if q is 0, q is suppose 0, so these two things q is 0 and these two things q is 0, then the output will be p bar into r bar, right. So here p bar is 1, r bar is 1, multiplied with the 1, it is a very good, and then p bar is 1, r bar is 0, that will output will be 0, right. Yeah, this is input is 1, sorry, p bar is 0, the output will be 0, and here also p bar will be 0, output will be 0. So the correct answer will be option A. So sometimes we can by using some actually intuitive analysis, or by looking at the truth table, we have, if we do some analysis, we can easily get to the answer. Okay, yeah. One more thing you can do, by in this equation you put each of the things, that is 0 0 0 and then 0 0 1, each of the things, and then you just calculate and see what is the output, but that is a very lengthy process. So you must first, at first you should do, what you should do, you should first simplify the Boolean expression into a much simpler form, and from there, by doing some analysis like what I have done, that it is q plus p bar r bar, that means whenever the q is 1, the output should be 1. The By this analysis only I have looked at each of the option, and then I choose the correct one. Okay, yeah. So this is the first question. Okay, yeah. So the second question, yeah, sorry, yeah. In the second question, which of the following functions is equivalent to the Boolean function this? Okay, so A is nothing but w plus w bar x, okay, plus z plus z bar w plus w bar x. Okay, yeah. So you have to simplify this thing. Okay. So at first we are seeing one thing, that w plus w bar x, this thing is common in both the terms, in these both the terms. So we are taking this thing common. Okay. So w plus w bar x, we took it common. So we get 1 from here plus z bar from here. Okay. And plus z as it is, right? This z. Okay. This is z. Okay. So you know 1 plus something results in 1. So w plus w bar x multiplied with 1 plus z, that will be the thing. Okay. So this can be written as w plus w bar x plus z. Okay. Now we have already discussed this law, which is this thing, distributive law. If there is a plus bc, then that can be written as a plus b plus a plus c into a plus c, right? We have already discussed this thing, that if we have a plus bc, then we can write as a plus b into, so, yeah, a plus c. So this is the distributive law. Yeah. So same thing if we use here, we get w plus w bar into w plus x plus z. Now w plus w bar, it is 1 according to the Boolean law. Multiply the w plus x plus z. So that means it will come as w plus x plus z. So this is the simplified Boolean expression. It cannot be simplified further. So this is the ultimate answer. So the correct answer will be w plus x plus z, which is answer B. Okay. This was pretty simple thing. Okay. Okay. The next problem. So the next problem is, which of the following functions is equivalent to the Boolean function this? Okay. So you have to simplify this Boolean function. So x is equal to pqr whole bar into p bar plus q bar plus r bar. Okay. Sorry, pqr. Okay. So now we should use the De Morgan's law. Okay. According to the De Morgan's law, we have already discussed this De Morgan's law. Like if there is some input a b c d, infinite input with bar, then we can written as a bar plus b bar plus c bar plus d bar plus dot dot dot. Second thing, a plus b plus c plus d plus everything bar, then it can be written as a bar dot b bar dot c bar dot d bar dot. Okay, so here it can be written as similarly p bar plus q bar plus r bar. Okay, it is a single bar. Okay, this is q bar plus r bar. Okay, and this can be written as p bar multiplied with q bar multiplied with r bar. So it will be multiplied with this thing, so it will be p bar multiplied with p bar q bar r bar plus this will be p bar into q bar into q bar into r bar plus this will be p bar into q bar into r bar into r bar. So this p bar into p bar, that means only p bar, then q bar, then r bar, then it is q bar into q bar, which is nothing but only q bar. This is r bar into r bar, which is nothing but only r bar. So if we add these three things, we know that a plus a is nothing but a. Similarly, a plus a will be nothing but a. So these three things will combine to get p bar q bar r. So the correct answer will be option A, p bar q bar r. Understood? So at first we have used the De Morgan's law here and here, and then we have just multiplied with this, and we know that p bar into this p bar becomes only p bar. So these two things becomes p bar, these two things become q bar, and these two things become r bar. And then we are adding the same thing, the output will be the same. Okay, yeah. Next question. Consider a logical function y is a function of a, b, c, d, the four variable. We want y equal to 1 for a, b, c, d these things, and for this thing y is don't care. For all other input values y is required to be 0. What is the minimum Boolean expression for y? So one thing, using the Boolean expression or some Boolean algebra, we can minimize the Boolean expression to a compact form. So similar is the thing for the K-map. Now we are introducing K-map. So K-map is also used to minimize the Boolean expression or the Boolean function. To minimize the Boolean function or Boolean expression, K-map is used. Okay, so if we draw the K-map, so it has four variable. So this is AB, this is CD. Okay, so 1, 2, 3, 4. Okay, that will be 1, 2, and then 3, and then 4. So it will be 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1. That means there is only see one thing in the K-map what we do. So here it is 0, 0. So now this 0 changes to 1. Only one variable shift. Okay, it is 0, 1, this is 1, 0. So this 0 changes to 1. Okay, and then it is 1, 0. That means this variable changes to 0. So like this thing here also, 0 changes to 1 here, here 0 changes to 1, and here this changes to this. So that means that in this K-map we use the gray code. This is the gray code thing. That means only one variable can be interchanged. Okay, if it is 0, it turns to 1, and if it is 1, it turns to 0. Only one variable for each. Okay, yeah. So what is the case here? So here it is telling that y is equal to 1, the output is equal to 1 for ABCD 0, 0, 0, 1. So it will be 0, 0, 0, 1. So here I am just drawing this is another pen. Okay, okay. So 0, 0, 0, 1, that means this thing 0, 0, 0, 1, this is 1, 0, 0, 1, 1, 0, 0, 1, 1. So for this thing 1, 0, 0, 1, So 1001, this is this thing, and then 1011, 101. So this is the thing. Okay, and then for this thing it is don't care, 1010. So for don't care we use this symbol cross. Okay, 1010, and then 1011, 1011, this thing, but this thing is already 1, so we don't consider it as don't care, it is basically the 1. Okay, then 1110, so 1110, this is 1110, and then 1111, so this is the 11, and the rest other things for all other input values y is equal to 0. So this is 0 0 0 0 0 0 0 0 0. Okay, so now we need to get the minimum Boolean expression for y. So to get a minimum Boolean expression, we should form we should first see that if there is a group of 16 is possible or not. That means 16 literal or 16 boxes is possible or not. So here there is 16 number of boxes is not possible. Then we will see that whether it is possible to form a 8 number of groups or not. But here also there is no possible of 8 number of group. Then we will see that there is possible of 4 number of groups or not. Yeah, 4 number of groups are possible. So if we consider this thing, this 1 1 1 1, and here this thing 1 1, so using this thing there are 4 number of groups are possible. Now in these 4 number of groups, so here if we consider this part, that is 1 1, this part and this part, so what we get, y is nothing but so here it will be 1 0, this is 0 0, that means b is only constant, that is b bar, and then here it is c is d is also the same thing, this is d, and this is the b bar. Okay, so b bar d, this thing. Okay, b bar d, and one more group is also possible, which is this thing, using this don't care. Okay, so this can be written as 1 1, that means a, and here this is 1 1 1 0, which is the first one, that is c, ac. But here see, in the first group all the ones are already taken, so we have to use the don't care term when only we need to consider all the one, but as all the ones are already covered in the first group, so we need not to consider the second group. Okay, if there is if suppose there is a case where you have to include don't care term also, that is the cross term also, to include someone to make a big group, then you can use. But here in the first group only all the ones are already covered, no ones are left out, so that means only this b bar d is sufficient to make this Boolean expression work. Okay, so ac will not be the answer, the correct answer will be only b bar d. So this will be the correct answer. So the correct answer will be this thing, this will not be, remember this thing. Okay, and rest other options are all false. Okay, yeah, obviously false. Yeah, okay, then the next thing, yeah, so for the digital circuit shown in the figure, which of the following expression correctly describe the function y? So this is basically a mask. So mask is nothing but multiplexer. So suppose there is a switch which is S, and here is the input A, and here is the input B, and this switch is correspond to 0 and this is 1. Okay, so the output we can say that whenever the switch, this switch select this 0, then the output is connected with this B. Okay, so the output will be whenever the switch is 0, that means S bar, the output will be B, that is the B thing, correct. And whenever the S is 1, whenever the S is 0, then the output is connected with this, but whenever the switch is becomes 1, that means this one is connected with this. So whatever in the A, that will be the output. So that means S into A. That means whenever S is 0, then 0 complement, that means 1. So that will allow the B to come to Y, right? Understood? Similarly, when the S is 1, so here it is written S 1. Whenever it is 1, then whatever is the input A, 1 into A, that means A, that will come into the output. That is why. So we can write like this. So here also, so this 0 and 1 is basically written as I0 and I1. Okay. So here also how we can write this thing, which are the following expression. So Y is nothing but x2 bar. That means whenever x2 is 0, then the output will be x1, right? X1 plus whenever the output will be 1, that is x2, then it will choose I1. I1 input is x1 bar. So this thing. So this is the basic example expression. So if we see this in a more detailed way, we can see that it is nothing but in the form of a b bar plus a bar b. That means it is nothing but a XOR of x1 and x2. Okay. So the correct answer will be x1 XOR x2. Okay, which is x1 x2 bar plus x2 x1 bar. So this is the correct answer. Okay. Next we move forward in the next thing. For the digital circuit shown in the figure, which of the following truth table correctly describes the function y? Okay. Okay. So here, if we want to write the expression, suppose we can do it in both the way. Okay, by doing some analysis and by doing some writing some expression. Okay. So suppose I am showing the method 1, which is a bit lengthier. If we write the expression, then how can we solve? Okay. So if we do this thing, so here I0 will be chosen, so y output will be y equal to, now I0 will be chosen whenever there is 0 0 in the input, 0 0, that means b bar c bar, then the input will go to output, right? So into 1 is the input. Okay, whenever this is 0 0, then this line will connect with this. Understood, right? Plus whenever this is 0 1, this is s1, right? S1 means that is the b is the first and this is a 0, right? 0. So that means with 0 1, then it will choose 1, that will choose a, right? 1. So that means whenever it is b bar, so b is 0 and c is 1, then it will choose a. Okay, plus whenever this is 1 0, then it will choose the I2, that is 1 0 means b c bar, right? B is 1 and c is 0, so c bar, and that will choose 0. Plus when it will be 1 1, then the output will be I3, right? So 1 1 means BC, then the output will be A bar. So if we write it in a more simple way, it is B bar C bar plus B bar A B bar C, right? Plus this becomes 0, this is a 0, and this thing becomes A bar B C. Okay. Yeah. Now you have to write each of the now you have to do each of the analysis, like if we put a 0 0 0, then what the output will come, if we put 0 0 1, then what will be the output will come. So you have to do this extensive analysis to get the correct answer or correct option or the correct truth table. Okay. Yeah, so this is the method 1, but I will do with method 2. Method 2 is some analysis. If you do in the digital electronics, it becomes much more simpler and it is a time saving techniques. Okay, so what I will do, see. Okay, okay, so what I will do, so I will see at first that the B and C, if it is 0 0, if it is 0 0, then the input is basically 1, the output is basically then 1. So if it is 0, the output will be 1. So this thing at first I will verify. So this is 0, output is 1, right? This is okay. Here also BC00 output is 1. Here also 00 output is 1. Very good. This is 00 output is 1 in both the cases. Here also it is 00, it is output 1. Here also it is 00, output is 1. So here BC is 00, output is 1. BC is 00, output is 1. Okay. Here also, so it seems that any of the option may also be correct. So we are not sure about the correct option yet. Okay. Yeah. So the next thing we'll see that suppose S1 S0, this will be 0 1, then whatever is the input, that will be the output, right? What will be the A, that will be the output. So this is the 0 1. Okay, so this is 0 1 and this is the 0 1. So whatever is the input A, that is the output. So till now this is right, till now this is right. Here this is 0 1, here this is 0 1. So till now this is right, till now this is right. Here also it is 0 1, here also it is 0 1. Till now this is whatever is the A, that is the output. It is also 0 1, it is also 0 1. So whatever is the input, that is the output. Okay, yeah, till now it's fine. Okay, the next thing, if BC is 1 0, 1 0 means this thing, if it is 1 0, then the output will be 0, right? Because the 0 is going to Y. So here the output is 1. So this is the wrong thing, this is the wrong thing. So this option will be wrong. Okay, here also it is 1 0, the output is 0. Okay, this is the 1 0, the output is 0. So till now this is okay. This is 1 0, the output is 0. Till now this okay. 1 0, the output is 0. Till now this is okay. It is 1 0, output is 0. Okay, till now 1 0, the output is 1. So that is not the case. So this will not be answered. The correct option will be option B or C. Now we'll see the fourth thing, that is if it is 1 1. So if it is 1 1, if it is 1 1, if it is 1 1, then whatever is the input, that will be complemented, right? Here it is 0, that becomes 1. Sorry, so this option is already not correct, we will not consider this thing. Okay, so we'll consider only these two, 1 1 and this is 1 1. So when it is 0, it is 1, when it is 1, it is 0. So it's coming as a complement, right? A bar. So this is the right answer. But here it is 1 1, whatever is the input, that is coming as the output, that is not, it should be complemented, right? Okay, so this is the wrong, so this will be wrong. So the correct option will be option B. So by doing this easy analysis, we can easily see that which of the options are correct. Okay, okay, I am moving to the next question. Here also the same thing, consider the truth table given in the figure. Which of the following implements can be used to realize the logic function y? So here similar is the thing, that is the marks here. So at first we will see that what can be the answer. Okay, so here at first we'll see this thing. Okay, so at first ABC, these three things are 0 0 0. Okay, so this thing are 0 0 0, that means the output will be 0. That means if ABC is 0 0 0, whatever will be the output will be 0 irrespective of D. So it is connected to 0, so that is right thing. This is right, this is right, this is right. Okay, the next thing, okay, if it is 0 0 1 and this is 0 0 1, this thing, then the output will be 1. Okay, that means the next thing, it is connected with 1, it is connected with 1, it is connected with 1, it is connected with 1. So far so good, all the options are matching. And now this is 0 1 0, 0 1 0 means this is the 2. Okay, so now we can easily see that it's the toggling. Okay, if it is 0 1, this becomes 1 0, which is toggling. So that means this should be D bar. So here it is D bar, sorry, this thing D bar, this is also D bar, this is also D bar, but this is D. So this not be the answer. So option D will not be the answer. Next, it is 0 1 1. Okay, the fourth one. So we can see that whatever is the input, that is the output, which is basically the buffer or the same thing. So that means the D, it will connect the D, it is connect the D, it is connecting the D. So far so good. Now 1 0 0 1 0 0, that is the next. So if there is 1 0 0, we can see the output will be 1 irrespective of this here y is 0 irrespective of D. Okay, and here y is 1 irrespective of D. Similarly here y equal to 1 irrespective of D. Okay, this is 1 0 0, right? 1 0 0 means I4. Okay, so I4 is 1. So 1, it's okay, it is also okay, it is also okay. Okay, the next thing is 1 0 1. So here what will be the input? It is toggling. Okay, 0 1, it is 1 0. So it is again toggling. So that means here it will be D bar. Okay, so here it is D, so it will not be the answer. So option A will not be the answer. Here it is D bar, here it is D bar. The next thing, if we look, this is 1 1 0, this is 1 1 0, that means it is 6. So whatever be the input, irrespective of that, output is equal to 0. So y equal to 0 irrespective of D. So irrespective of the output is 0, so the this one will not be the answer because it is 1, so it should be 0. So C will be the right answer. If you see the last one also, it is 1 1 1 1 1 1. So here also the y is equal to 1 irrespective of D. Y is equal to 1 irrespective of D. That means it will be 1. Yeah, the last one is 1. So the correct option is answer C. Okay. Yeah. Okay. So far so good. Yeah. So now we have to consider this thing. Okay, so I am moving forward to the next question. Yeah, so here the input is A. So here there are basically three NAND gates and they are connected with this input. So what will be the expression of the output? Okay, so here there is A and it is C bar because it is NAND gate but the input is same, so it will be C bar. Okay, and this is the B. So in this point the output will be A into C bar whole bar. Okay, the NAND gate. And in Y, this Y should be A into C bar, this bar multiplied with B total bar. Okay, this. Now we'll use the De Morgan's theorem. Simply A into C bar and again bar plus B bar. Okay, and now this 2 bar becomes A into C bar plus B bar. Okay, so this is a simple thing. So the correct answer is option A, right? So basically what we did, we just, so here it is A, here it is C. So C is the only input in the two input NAND gate, so it will be C bar, and here it will be B. So it will be A into C bar, then bar, and it will be A into C bar into multiplied with B whole bar. So use the De Morgan's law, and we simplified this thing, and then we have reached the answer. Okay, yeah. The next question, yeah, here for the digital circuit shown in figure, which are the following expression correctly describe the function? Oh, the similar is the case. So here it will be A bar. Okay, here it will be B, here it will be B bar, here it will be C bar. So it is the NOR gate. So here it will be A bar plus B total bar, and here it will be B bar plus C bar total bar. Okay, and here it will be, so if we call it y dash, so y dash will be, sorry, so y dash, that will be a bar, sorry, a bar plus b total bar plus b bar plus c bar total bar, this bar. So if we simplify this thing, a bar plus b this bar and bar multiplied with b bar plus c bar this bar and bar. Okay, so this thing. Okay, so this will be a bar plus b multiplied with b bar c bar. Okay, okay, so that will be this. Okay, and if we consider this as y is nothing but a bar plus b whole bar plus b bar plus c bar this whole bar with this bar and another bar, that means a bar plus b whole bar plus b bar plus c bar whole bar. Okay, so that means it will be a bar dot b plus b bar dot c bar. Okay, so this will be a b bar plus bc, a b bar plus bc. So the correct answer will be option D. Okay, you understood it, right? Because this here till here this is the bar, and till here this will be the complement of that whole thing. So these two bar gets cancelled out and it becomes a bar b, a bar plus b whole bar plus b bar plus c bar whole bar, right? And if we use De Morgan's law over here, so a bar dot b bar plus b bar dot c bar. So a bar means a into b bar, this b bar, and this is b and this is c. The correct answer will be option D. Okay, so moving to the next problem, for the digital circuit shown in the figure, which of the following expression correctly describe the function y? Okay, so it is basically going here, it is p, it is q bar, and here it is p bar, and here it is q. So it will be p q bar and it will be p bar q, and then we are using NOT of that. So y will be p q bar plus p bar q and then NOT of that, this thing. So these are the, what I have already discussed, these are the XOR gate. This is the XOR gate expression, and NOT of that will be the XNOT gate. XNOT gate means, and this will be PQ plus P bar Q bar. So I told earlier that I will prove this thing. So now I am proving. Okay, so the correct answer will be this thing, PQ plus P bar Q bar, right? It can be easily said, right? Because this is the expression of a XOR gate, PQ bar plus P bar Q, PQ bar plus P bar Q, this is the XOR gate, and complement of that will be nothing but the XNOR gate. And XNOR gate, we know that already, it is P XNOR Q is nothing but PQ plus P bar Q bar. But I will prove this thing now. So Y is basically PQ bar plus P bar Q this whole bar. So that means if we use De Morgan's law, so this will be this thing. Now it will be P bar plus Q, if we express this thing, Q bar into P double bar plus Q bar. So that means it will be P bar plus Q multiplied with P plus Q bar. So it will be P bar dot P plus P into Q plus p bar into q bar plus q into q bar. Now this p dot p bar, it becomes 0, and q dot q bar, it also becomes 0. So that means pq plus p bar q bar. Okay, understood? So this means that p XOR of q, this complement is nothing but p of x naught of q. Okay, so the correct answer will be option A. Okay. Okay, the next thing. Consider the truth table given in figure. Which of the following expression correctly describes the minimal sum of product form of the logical function this? Okay. Okay. So here it is a y is a four variable. Y is a function of four Boolean variables. So we can use a K map and we can easily solve the problem. Okay. So here we are using the K map to solve the problem. This is AB, this is CD, 0 0 0 1 1 1 1 0. This is also 0 0 0 1 1 1 1 0. So okay, see which are the options are 1. See at first 0 0 0 0, this is 1, this one is also 1, this one is also 1, this one is 1, this one is 1, and then rest of the things are 0. Okay, so if we put 1, so 0 0 0 0, that means this one. So this thing is basically 1, 0 0 1 0, so 0 0 1 0, this is 1, 0 1 0 0, 0 1 0 0, 0 1 1 0, 0 1 1 0, this is also 1, and 0 1 1 1, 0 1 1 1, this is also, okay, and rest other things are 0. Okay, so rest other things are 0 0 0 0 0 0 0 0 0 0 0. So what I have already discussed, that see whether it's possible to form 16 number of groups. A group consists of 16 boxes. So 16 boxes not possible. 8 is also not possible. 4 it is possible. 4 it is possible like this. Okay, this is the 4 boxes. Okay, and next to so this 4 box doesn't include this one. Okay, to include this one, we see whether it's 4 boxes is possible. No, 4 boxes is not possible. So next what is possible is these two. Okay, these two. So one is like this thing, so this 1 1 and this 1 1, and another is like this thing, this 1 1. Okay, so if we write the expression, so y will be, so if we consider these two, so this surface which is a bar, and among these two this is fixed which is d bar, so a bar d bar, plus for these two things actually, this is a bar b, a bar b, and this thing will be only c. Okay, so a bar b c. So the correct answer will be a bar d bar plus a bar b c, which is option c. So this is the basic K-map problem, how we can solve this thing. Okay, yeah, so we move forward to the next part. Okay, okay. So this is the basically the timing diagram using which we can solve this problem. So here we have for the circuit of input waveform shown in the figure, which plot gives the correct output. So basically there are two input A, B, and this is a XOR gate and output is Y. So the output expression can be written as, we have already discussed, A XOR of B. A XOR of B means A bar B plus A B bar. So we have already discussed the truth table, right? So what we have already discussed, if there are unequal inputs, then the output will be 1, right? If this is 0 1, this is 1 0, then the output will be 1. Okay, so here at first we need to write what is the input. Okay, input waveform. So this is 0, this is 1, this is 1, this whole thing is 0, this is 1, this is 0, this is 1. Similarly here it is 1, it is 1, it is 0, so it is 0, it is 0, it is 0, it is 1, and it is 1. Okay, so when the output will be 1, so here it is 0 and 1, so this output will be 1. Okay, 0 and 1, so this output will be 1. Similarly here it is 1 and 0, so this output will be 1. Okay, here we have 1 and 0, so this output will be 1. Here also we have the output will be 1. Okay, so the correct answer will be, so if we plot here, we get, so 0 and 1, that means this is 1, and then again here it will fall to 0. Okay, 0. Now here only it will become 1. Okay, so here only it will become 1, and it will move, and then it is becomes 0, and then here it is 1, right? Here 0 and 1 becomes 1, then it will become 0, and then it will again become 1, and then it will become 0. So this is the correct waveform, this thing, right? Option C. Understood, right? So 0 and 1, that makes it 1. This is 1 and 0, this makes 0. This is 0 and 1, this makes 1. 0 0, this makes 0. 0 and 1, this makes 1. 0 0, this makes 0. 0 and 1, this makes 1, and 1 and 1, this makes 0. Okay, so this is the correct answer. The correct answer will be option C. Okay, okay. Next question. If the logical function y is given in the truth table is written in a minimum sum of product, which of the following term will not appear in the expression? Okay, in the expression, which of the term will not appear? Okay, so okay, so we have to apply the same concept, which is k map. So I am drawing the k map at first. Okay, so here it is AB, this is CD, 0 0 0 1 1 1 1 0, right? Here also 0 0 0 1 1 1 1 0, right? Okay, so now see which of the options y is 1. See, for this thing it is 1, for this thing it is 1, for this thing also it is 1, for this thing is 1, this is 1, for this is 1. Okay, so these things are 1, this is 1, this is 1, this is 1, and this is 1. Okay, okay, so write it at first. So 0 0 0 1, that means this thing is 1. Then 0 0 1 1, so 0 0 1 1, this thing is 1. Then 0 1 0 0 0 1 0 0, this thing is 1. 0 1 0 1 0 1 0 1, this thing is 1. 0 1 1 1 0 1 1 1, this thing is also 1. Then 1 1 1 0 1 1 1 0, this thing is 1. Okay, now what are the don't care terms? Don't care terms are this thing, So what is the don't care terms? So don't care terms are this thing x, this thing x, this thing x, and this thing. Okay, so if we consider this thing, so it will be, so 1001, so 1001, this is cross 1011, 1011, this will be cross 1101, 1101, this will be cross, and 1111, so this will be cross. Okay, yeah. So see how much so so what are the group that we can form easily, we can see. So here we can form this group using this 8 number of things. This group is possible. Okay, so that means it is what, so a b both are changing, only the d is fixed, so that means only d here. If we consider this thing 1 and 1, then we can get this thing is a bar, then b, and then here it is c bar, a bar b c bar. Okay, and similarly here if we consider these two things, then we get this thing is ab, and here it is only c, right? So a b c. Okay, and then if we consider this thing, if we consider this group only, because this group covers all ones and no don't care term, then we get with this group it is a bar and d. Okay, a bar d. So basically here what are the things, a bar b c bar, this is covered, so this not will be the answer. The question is what does not appear in the expression. Okay, so a bar b c bar that will appear. Then what is the thing, abc, right? So abc will also appear, so it will not be the answer. Then d and or a bar d. Okay, so a bar d, it will not appear in the answer. The correct answer will be b d. But the correct answer will be b into d, that will not appear in the answer. Okay, so this was pretty much the easy thing. Moving forward to the next question. In minimizing the logic function y given in truth table, how many of the don't care condition need to be treated as 0? Okay, how many of the don't care condition need to be treated as 0? Okay, that means how many don't care term we does not include in a group, right, in forming a k-map group. Okay, so at first I will draw the k-map expression. A B C D, this is 0 0 0 1 1 1 1 0. Okay, and then here also it is 0 1 1 0 1 1 1 0. Okay, yeah. Now what is happening, this is 0 0 0 1, this is 1, this is 1, this is 1, this is 1. Okay, then this is 1, and then this is 1. Okay, so what are the things, 0 0 0 1 0 0 0 1 0 0 1 1 0 0 1 1 0 1 0 0 0 1 0 0 0 1 0 1 0 1 0 1 0 1 1 1 0 1 1 1, and then 1 1 1 0, that is 1 1 1 0. This is the thing. Okay, now we'll consider about the don't care terms. Don't care terms are this is the 1 2 3, and this is the 4. So it will be So 1001, so 1001, this is a don't care. Then we have 1011, 1011, this is the don't care. Okay. Then 1101, 1101, this is the don't care. And then it is 1111, so this is the don't care. Okay. Yeah. So see, so now we have to form a group. Okay. So we can see easily that if we consider this 4, this one is not needed, this don't care are not needed to form a group. So if we consider this, so we get, this is a bar, right, a bar, and then we get d. Okay, a bar d, right, from here. Yeah, this is a bar and this is d. Okay. Yeah, if we form this thing, then we get, to form this thing we get a bar b, and then it is 0 1 and 0 0 0 1, right, and this is 1 1. Okay, 1 0, so this will be c bar. But to form this thing a group, one don't care we need to take, right, to form a group. So from here we get a b, and then here it will be c. Okay. Yeah, so rest 3 don't care we should not consider, so it can be considered as 0, right. So this thing and this thing, it should be considered as 0, but these don't care we need to include to make a group. So the correct answer will be, out of the 4 don't care condition, 3 needs to be treated as 0. So answer will be option C. Okay. Okay, fine. So moving to the last question. So this is the last question. In the circuit given in figure, which option correctly describe the logical function of x? So we have already discussed this kind of problem. Okay, see one thing. At first we need to find out what should be the expression. So here it is XOR, right? A XOR B. That means A B bar plus A bar B. That is the thing. Here till here it is B X not C, right? So BC plus B bar C bar. Okay, and here it is C. So what will be the expression is? S is nothing but, if we multiply this thing A bar B, this thing multiplied with BC plus B bar C bar multiplied with C. So what it's coming, if we multiply this thing, so A B bar into B into C plus A B bar into C bar. Okay, plus A bar B into C plus A bar B bar C bar. Okay, this thing, whole thing will be multiplied with C. Okay, so now B bar into B, that makes it 0, and here it will get A B bar C bar plus, right, from here we get A bar B, sorry, sorry, here we get A bar B C plus, here we get also 0, this is also becomes 0, this becomes 0, right. So this thing multiplied with C, multiplied with C, so that means A B bar C bar into C plus A bar B C into C. So this becomes 0 again, so it becomes ultimately A bar B C. So x equal to A bar B C, this is the correct Boolean expression, x is equal to A bar B C, right. So now what will be the output? C. So here if we consider this thing, that means it is 0 1 0 1 0 1 0 1, okay, and it is 0 0 1 1 0 0 1 1, okay, and it is 0 0 0 0 1 1 1 1. So what is the output? The correct output will be, it is basically the x will be 1 when a bar, b, c all are 1 at a time. At a time all are 1. That means a bar is equal to 1, b is equal to 1, c is equal to 1. So this implies that a is equal to 0, b is equal to 1 and c is equal to 1. So where it is 0 1 1, so we can say it is 0, this is 0, this is 1 and this is 1. Only this condition the output will be 1. So here the output will be 1. Right? You understood, right? Yeah. So in the other case, it is 1 for 2 cycle, that is not possible. It is 1 or 2 cycle, this is not possible. This is also 1 whenever the 3 output is 1 1 and 1. So that is also not possible. So option D, option C and option B are not possible. Option A is the correct answer, right? Understood, right? So these are the things. So we can easily use some concept, basic Boolean algebra equations, and by matching the answer and also doing some intuitive analysis, you can easily get to answer and save much more time. Actually, to solve this each of the question, we need only just uh, 15-20 seconds. It's enough to solve the all the questions. So it's a very scoring subject, digital electronics, and it's a very easy one. If you have captured this digital electronics once, then it will be very helpful for you to attain a good number of marks. Okay, so okay, that's all for today. So I am stopping the recording. Okay, okay, so thank you all. We'll meet again on the next Tuesday, usual time. Okay, bye.